Hi, today we'll be talking about the angle bisector theorem, which is a handy tool in geometry that can make solving triangle problems a whole lot easier, especially if you're just working with a single triangle. With this angle bisector theorem, you can bypass similarity, you can bypass congruence, you can bypass all those cumbersome methods of checking to see if you can compare sides, create ratios, and use a simple, pretty easy formula. So first of all, what is the angle bisector theorem? And when can I use it? So essentially, an angle bisector in a triangle divides opposite sides into two segments which are the same in proportion as the other two sides of the triangle. So let's put this in plain English, right? This right here is my angle bisector. And when I draw an angle bisector, I split the opposite side, right? So this whole side here, into two segments, which are proportional to the other two sides of the triangle, right? So the ratio between A and B is the same thing as the ratio between C and D. So we can write this formula we see right here. And we call it an angle bisector because it takes an angle and it splits it into two equal parts. That's why we see we have this little line that usually means equal. You also see it written like this sometimes. Essentially, right, an angle bisector makes two lines equal. It's important to make sure and remember that angle bisectors are different from other types of lines, especially perpendicular lines, which will form a right angle. We cannot draw a right angle here, right? These do not necessarily create right angles. The only thing that they're guaranteed to do is split an angle into two and create this ratio here. And you might say, well, okay, that's an interesting tidbit, but how can we use it? Well, it's very, very handy for quite a lot of problems. Now, let's do an example here. I'm going to keep this formula up because we're going to need it. And let's do this problem, right? So imagine we're presented with a triangle, right? Right. And they've drawn a little dotted line. And so I said if we draw this dotted line, this angle here will be split into two equal parts, right? Two equal parts. Right away I'm thinking angle bisector, right? And they tell you that this length right here is 2. This length right here is 3. This length is 6. And this length is x. Now, this is not necessarily to scale, but we want to find the value of x. Now, this would be especially hard if we try to do it a traditional way, right? We obviously don't have a right triangle, so we can't use the Pythagorean Theorem. I don't see any other triangle I can use similarity rules to find the answer, and frankly, I don't see any similarity rule that I can use much between this triangle, right? Because we know these angles are equal, but we know that these sides aren't. We don't know if these angles are equal either, so we can't do angle or side similarity. But we can use the angle bisector theorem, right? We know that 2 over x, right? This is our A and this is our B. This is our C and this is our D, is equal to 3 over 6, right? So 2 over x, I'm going to simplify that, is equal to 1/2. And now we can cross multiply and we see that 4 is equal to x. So x is 4. And see, they're just using this simple ratio from the angle bisector allowed us to solve a problem that would be extremely difficult to do using almost any other strategy. And we can apply this to a whole lot of other stuff too. Let's say we have another triangle, right? But this time, we know the entirety. First, let me draw my angle bisector. They give us this. They'll say it splits it into two congruent angles. This length is 5, this length is 7. This entire length from here to here is 10. And we want to find this distance here. And this might seem especially difficult given that we don't have many of the tools we would like to have at our disposal, right? We can't, in the last problem, we knew one of these sides, right? In this problem, we don't know any of these sides, right? We don't know what this length is. We can represent it algebraically, and that's going to be key to solving this problem. This length here, right, is going to be 10 minus x. Why? Well, the total length from here to here is 10. Right? And if I add x and 10 minus x, I'm going to get 10. So I'm going to get the total length. That's why it's 10 minus x. But how does that help us? Well, when you write the angle bisector theorem for this problem, x over 10 minus x is equal to 5 over 7, we actually have an equation we can solve. And you might say, well, why is that? Well, when we cross multiply, we get an equation where all our terms are either numbers or they're in terms of x, which means we can solve our problem. So, we have 7x is equal to 5 times 10 minus x. I'll distribute out this 5. 7x is equal to 50 minus 5x. I'm going to add that 5 here. 12x equals 50. So x equals 50 over 12. That's my final answer right there. And once again, the angle bisector theorem made solving that incredibly easy. We didn't have to use any complicated similarity rules or use any weird, funky right triangle messes. We were able to use a simple proportion, a simple ratio, and solve our problem pretty quickly. So, to go over again and help you remember, you're dealing with the angle bisector, and you can apply an angle bisector theorem when there's a line that splits an angle into two congruent or equal parts. Right? You see that, you know you have an angle bisector. What do you do from there? Well, the portions of the line that it splits, right? This are proportional to the same positions on other sides, right? So A over B is equal to C over D, right? This length over this length is equal to this length over this length, right? So basically, the ratio between the corresponding positions is going to be the same. The corresponding lengths, I should say, not positions. And that is the angle bisector theorem. I hope that helped. I hope you found that useful, and I hope you have a great day.